Welcome to the Deep Dive, where we take complex research, analyze the sources you provided, and give you the fast track to expertise.
Today, we are wrestling with a really fundamental argument about the future of artificial intelligence.
Yeah, we're diving into a research position from some influential voices, including researchers from NVIDIA and the Georgia Institute of Technology, and they're arguing for a complete structural shift in how we build AI agents.
And that shift is, it's pretty dramatic.
Mhm.
Historically, bigger has always been better, meaning large language models, or LLMs, have dominated the conversation.
But these sources are making a really provocative case.
They are. They're saying we have to move away from these centralized LLMs and really embrace specialized small language models, SLMs.
So our mission today is to unpack this core thesis.
Exactly. The idea that SLMs aren't just an alternative, but an operational and economic necessity for the next generation of agentic AI.
Okay, so let's jump right into that central idea. The very first slide here, the headline, it's a simple, stark declaration.
It is. Small language models are the future of agentic AI.
That really challenges the reigning paradigm, doesn't it? If LLMs are capable of everything, why would we even need smaller, specialized models?
Well, the implication is that these current monolithic systems are fundamentally inefficient.
They're misaligned with what agents actually do in a real industrial setting.
Precisely. The thinking behind this whole position is about a structural change, moving from a single centralized generalist to a decentralized network of specialized experts.
It's like switching from a single, massive mainframe computer to a distributed network of microservices.
That's a perfect analogy.
So why is this conversion so urgent right now? The next slide here gives some crucial context on the market momentum.
It does. Agentic AI is it's not a research experiment anymore. It's moving into the mainstream at a blistering pace.
And these growth stats really confirm that urgency.
Yeah. The market for agentic AI is projected to reach a massive $200 billion by 2034.
And to put that in perspective, that's up from just over $5 billion in late 2024.
It's explosive growth. And it proves these systems are expected to play a huge role in the modern economy, like almost immediately.
And it's not just a projection, it's already here. The sources note that over 50% of large IT enterprises are already actively using AI agents.
And get this, 21% adopted them just in the last year alone.
Wow.
But here's the critical point, and this brings us to slide 3. The core components powering most of these agents today are still very large language models.
Which the researchers describe as a monolithic model.
Exactly. This slide shows the industry standard architecture, and it's centralized, generalist, and incredibly resource intensive.
Okay, so let's break down the components of this standard model. First, they say, is the singleton choice.
Right. Meaning every single agent relies on one single LLM API endpoint for all its reasoning, all its tool use, everything.
And second, that LLM is generalist by design.
It's built to handle everything from,
Yeah.
philosophical debates to complex code generation.
And critically, this reliance has created a huge sunk cost. The source estimates this standard architecture underpins an estimated $57 billion investment in hosting infrastructure globally.
That is a staggering number.
It really is, and it makes the visual on this slide so clear. You have these 6 different agent apps,
Doing everything from calendar management to inventory logging.
and they're all funneling their requests into one enormous gray LLM cloud via a single expensive API call.
It's a single point of failure and a single point of extreme cost.
Which leads directly into slide 4 and the core problem the paper identifies. This dominance is a fundamental misalignment.
Yes, a misalignment of resources and requirements. The thinking here is to really establish that friction point between what the monolithic LLM offers and what the actual agent task demands.
I get that. An LLM offers impressive generality, right? The ability to hold a flowing, nuanced conversation.
Sure.
But if I'm building an agent to automate, say, mundane, repetitive office tasks, am I not just severely overpaying for that generality?
Yeah, you absolutely are. That's the key insight. The LLM is like a giant gear trying to mesh with a much smaller gear, the agent task.
So while the LLM provides philosophical depth, most actual agentic use cases are, well, they're practical.
Overwhelmingly practical. They're repetitive. The same few functions are called thousands of times a day.
They're scoped operating in a narrow, well-defined domain, like just extracting invoice data.
And, maybe most importantly, they are non-conversational.
Machine to machine.
Exactly.
Hmm.
They require strict, reliable formatting, usually clean JSON or perfectly structured code, not human-like fluency.
So if you're relying on a massive, expensive, and sometimes unreliable generalist model to repeatedly do a narrow, structured job,
You're systematically misallocating computational resources.
Yeah.
The conclusion here is just inescapable.
Mhm.
The status quo is economically inefficient and, at scale, environmentally unsustainable.
and this is where the argument on slide 5 shifts from cost to capability, because that's often the biggest hurdle for SLM adoption, right? The assumption that size equals capability.
It is, but the researchers provide some really concrete counter-evidence. The proof is in the performance. Small models are already capable enough for the job.
So capability is decoupling from parameter count.
It absolutely is, thanks to modern training techniques and specialized augmentation. The examples here are powerful. Look at XLM28B.
Okay.
It's a relatively small model that actually outperforms frontier models like GPT-4o and Claude 3.5 on tool calling accuracy.
Wait, hold on. You're saying a tiny model is better at using tools than the newest, most massive generalist models? That completely flips the script.
It does, because for an agent, tool calling accuracy is the most vital metric, not whether it can write poetry.
Right.
And it's not an isolated finding. Look at Phi-2, which is only 2.7 billion parameters. It achieves reasoning and code generation scores on par with models 10 times its size,
The 30 billion parameter cloud.
while running about 15 times faster.
15 times faster. So the crucial realization here is that the binding constraint is now capability, not the sheer parameter count.
And if you can achieve the required functionality with a small model, the argument becomes purely economic.
Which brings us to slide 6, the overwhelming economic case for SLMs. The thinking here seems to be about quantifying that advantage in hard numbers.
It is. And the quantification is dramatic. Serving a 7 billion parameter SLM is 10 to 30 times cheaper than serving a 70 to 175 billion parameter LLM.
And that calculation covers latency, energy consumption, and FLOPS.
And for listeners who don't spend all day reading compute specs, FLOPS just stands for floating point operations per second. It's a measure of raw computing power.
So when we say an SLM is 10 to 30 times cheaper across FOPS, we mean it needs 10 to 30 times less pure computing power to get the job done.
Exactly, and that saving translates into 3 huge business advantages.
First, immense inference efficiency, so real-time responses without the high operational costs.
Second, and this is a revolutionary advantage for rapid deployment, is fine-tuning agility.
Okay, so explain that. What does that mean in practice?
It means if you need to fix a bug in your agent or add a new skill, you don't wait weeks for a massive retraining. Behaviors can be added or adjusted overnight. We're talking a few GPU hours.
That ability to adapt is a total game changer. And the third point is edge deployment.
Right. Because SLMs are so small, they unlock real-time offline inference on local hardware.
Like ChatRTX running directly on a laptop.
Precisely. Which radically lowers latency and crucially gives enterprises control over their data. It never has to leave their protected environment.
So it's not just about savings. Slide 7 makes the architectural argument that SLMs are just structurally a better fit.
Yes, they're inherently more suited to the modular nature of agentic systems.
The sources outline 3 core concepts here. First is narrow functionality. A fine-tuned SLM is a direct, precise tool for one job.
And it stops the generalist model from wasting resources on skills it doesn't need in that task.
Second is strict behavioral alignment.
This is key. Since agents communicate in structured formats, you can train a specialized SLM for perfect, reliable formatting.
Which cuts down on those frustrating LLM hallucinations when, money or critical data is on the line.
Absolutely. And third is natural heterogeneity, the composite system.
We don't have to throw out LLMs entirely.
Not at all. They can become what they're best suited for. being a high-level orchestrator deciding the overall strategy.
While the specialized SLMs execute the specific, repetitive, low-latency subtasks.
Exactly. The slide illustrates this perfectly, contrasting the two workflows. In the old language model agency flow, the LLM does all the heavy lifting,
But in the better code agency flow, a simple controller manages the calls.
and it delegates tasks to a mix of specialized tools, SLMs, and only calls the big, expensive LLM for that initial, truly complex reasoning step.
It distributes the load and the cost. It makes perfect sense.
It does.
But I have to play devil's advocate here, which I think brings us to slide 8. Does general understanding really outweigh specialization? The source acknowledges this pushback.
It's the core of the LLM evangelist's argument, that an LLM's vast semantic hub of general knowledge is essential.
But the researchers have a powerful rebuttal. First, they say architecture matters.
Right. Scaling laws assume a fixed architecture, but SLMs can use novel, size-specific designs, like Mamba hybrids.
Okay, can you break down what a Mamba hybrid architecture is in simple terms?
Sure. Think of most LLMs as needing to look at every single previous word to write the next one. That's the attention mechanism, and it's computationally expensive.
Okay.
Mamba hybrids are more like summarizing key points as you go. It's much faster and more efficient for processing long sequences, which let small models be exceptionally fast.
I see. So they're optimizing for speed and efficiency, not brute forcing general knowledge.
Precisely. And the second rebuttal is that fine-tuning is a game changer.
Hmm.
You can achieve the needed reliability for specific tasks cheaply and easily.
And the third argument, which I find most crucial, is that agents decompose complexity.
Yes. Agentic systems work by breaking a hard problem into a series of simple subtasks. And once you're executing those simple subtasks,
The LLM's enormous semantic hub offers very little utility. It's just expensive overkill.
it's exactly.
So if the performance and economic cases are this strong, the next slide asks the big question, why hasn't this happened yet?
And the hurdles they identify are practical, not fundamental.
They outline 3 main barriers. The first, and maybe the most powerful, is infrastructure inertia.
Billions have already been spent on centralized LLM inference. It creates a powerful bias toward the existing model. You don't just rip out infrastructure, you just spend a fortune on.
The second barrier is misaligned benchmarks.
Right. SLMs are often judged using benchmarks designed for generalist LLMs like conversational fluency, instead of metrics that measure actual agentic utility.
Like tool calling accuracy or low latency reliability.
So the market perceives them as less capable than they actually are for their target jobs.
And the third barrier is simply lack of popular awareness.
LLMs get the headlines, the marketing blitz. SLMs are the workhorses, but they lack the hype, despite being perfect for industrial use cases.
It's a battle of perception.
But fortunately, the researchers don't just point out problems, they provide a solution. Slide 10 is a practical roadmap.
The LLM to SLM agent conversion algorithm. A clear 6-step transition path.
Yep, designed to make the shift achievable for any organization.
It's a continuous cycle. Step 1. Collect. Securely log all non-PI data flowing into the LLM. Step 2. Curate. Filter and anonymize that into a clean dataset.
Then step 3, cluster. Use unsupervised techniques to find the recurring patterns, the simple jobs your LLM is doing over and over again.
Once you've found those jobs, step 4. Select a candidate SLM for each task. Then step 5. Fine-tune. Train that specialist SLM.
And the fine-tuning process relies on these really efficient techniques like PEF and knowledge distillation.
Can you quickly clarify what those are?
Absolutely. PEFT is parameter-efficient fine-tuning. It lets you train a model by only updating a tiny fraction of its parameters. It's incredibly fast and cheap.
And knowledge distillation.
That's essentially using the big, smart LLM as a teacher. You have the small SLM mimic the LLM's correct output, capturing its refined behavior without all the bulk.
It transfers the skill without the baggage. Fascinating. And the final step, step 6, iterate.
You periodically retrain the SLMs with new data to keep enhancing performance and lowering costs. It's a closed-loop system for efficiency.
Which brings us to the final slide, the conclusion. The future of agentic AI is a composite system.
The core vision is clear. It's about a Lego-like composition of intelligence. Scaling out with a network of small, specialized experts is just better than scaling up one massive, monolithic model.
And these composite systems are cheaper, they're faster to debug because the failure points are isolated, and they're much easier to deploy and update.
The shift really does seem not just economically inevitable, but structurally superior.
And to connect this back to the broader implications, this shift directly addresses some of the biggest challenges facing the industry.
It does. By grappling with rising infrastructure costs and environmental concerns, adopting SLMs promotes responsible and sustainable AI deployment.
So what does this all mean for you as you're looking at the next wave of AI? This research gives you a robust, actionable foundation for challenging that bigger is better mindset.
You now have the tools to understand why those small models are actually the giants in agent performance.
And to leave you with a provocative thought, if SLMs do become the standard for specific repetitive tasks and they capture, say, 90% of the market share.
Where does that leave the big guys?
Exactly. How will the definition of general intelligence in AI need to change? And where will the LLMs that currently dominate the market find their enduring niche in this new modular ecosystem?
We're already seeing them settle into that high-level orchestrator role.
But is that enough to justify their cost? A fascinating future awaits.
Indeed.
We'll catch you on the next deep dive.